Hello. I thank organizers for the possibility to make this talk. Thanks a lot. And here I wish to present our data on the break junction study of samples of neodymium 1111 system. It's also belongs to the ferromarsenide system, but it has very unusual doping when doping goes with hydrogen substituting of the oxygen. So it's a rare type of doping, and here we begin. Here is the outline of my talk, and I have two experimental parts, but I'm not sure that time is enough for both of them. But as usual, we start with some introduction. As you know, the main blocks of the crystalline structure of iron arsenides is made of ferrum and arsenicum atoms, and it is the same in the compounds with rare earth, so-called 1111 because of chemical indexes in this formula, and the same one could say it for the most popular, probably most popular compound, barium 122. You see the same. It's constructed with ferrum arsenicum blocks. They shifted, but the difference only between them. So it's usual, and for the usual type of Fermi surface of 1111 compounds, one could predict. It was predicted some pockets and barrels in gamma points. So below the critical temperature of superconductivity, the large superconducting gap develops here, and also two crosses electron cylinders in M point. But in comparison to other 1111 compounds, these hydrogen substitutions gives very unusual phase diagram. For the 1 atmosphere pressure, you should see only the black lines, not the colored one. So it taken from this very nice work of Kobayashi et al. So you could see that superconducting phase develops between the two parent phase, and here near the edge of the magnetic and structural transitions, superconductivity develops. But it's very unusual for hydrogen doping because you see two domes here. From the other side, if you would apply pressure, and the data for the 6 GPa pressure is presented by the colored parts, you see that this dome combines to the one, and the maximal TC is nearly the same for others 1111 compounds. But it's very unusual from this type of view. The experimental data I will show you was obtained with the help of the planar break junction technique, which is used to produce superconductor constriction, superconductor, so symmetrical contacts. In general, one could produce Josephson contacts and SNS Andreev contacts, but typically for the iron base superconductors, it could possible only to produce Andreev contacts. One should take the planar or CAT planar sample in AB planes and put it to the springy holders. You could see the 4-lead connection, and it's from the one side it's very good, but and also from other side the current injection to the sample is done far from the break junction, and so generally we have no problems with overheating. Then if we try to bend this spring, and you will see what is typically happens for the layered materials and layered superconductors as well. So it's copper foil, and somehow we produce this stress, and we got splitting of the sample because we put it directly in a B plane, and C direction you see is perpendicular, so it splits to the typically to the layer and terrace structures, produce some net of the constriction. But nearly every time you have a possibility to apply the stress so that curvature of this experimental table produce only in the single contact to some terrace, one of terraces. And of course it's simply to understand that the high of any terrace is some natural number of the elementary layers of sample. But thus we are sure that the current injection goes directly in C direction. This animation was done for the single crystal, but the same will work also for the polycrystalline sample, and some sketch is presented there. Here you see the 3 example grains of the polycrystalline sample, and this red line is a direction of crack would be produced. But the orientation of layers, the key word here is layers. It will work only for the layered sample. When layers is parallel to the crack, the grain should be cracked, and in the opposite case, no. But what happened to the grain number 2? It should be cracked or not. It simply depends on the combination of the angle, AB planes angle orientation along the crack direction, and the ratio of the interlayer and intergrain strength, which how strongly connected this grain to its neighbors. Then it could be also broken or not. And here you could see some electron microscopic photo for the gadolinium 1111 polycrystals, and the rectangular some rectangular marks shows the cracked polycrystalline. As for the blue one, you could see its zoomed version, and you could see layers and terraces. The same for other 1111 samples with samarium. We could estimate typical contact diameter as from 8 to 80 nanometers, and this is less both, of course, the crystal grain and the terrace width, so it should be as 1 point at at some terrace. So planar break junction technique allows to work also with the layered samples, and it produces good heatsink from the constriction, because this point connected with bulk from the upper and from the lower sides. It's a good heatsink. Possible to mechanically readjust the contact geometry. Several spectroscopic techniques, I mean Josephson, intrinsic Josephson, Andreev, and so-called intrinsic Andreev spectroscopies. And it gives the local probe of the bulk superconducting gap when we work to the all bulk of this step. Two words on the classical multiple Andreev reflection effect spectroscopy. Probably I have no time to say long on this, but I just wish to emphasize that every time if we compare current voltage characteristic of the classical SNS contacts with Z with the temperature more than Tc, it has an excess current and some subharmonic gap structure. But the transport is incoherent, so called long contact regime, as gives and as okay for inelastic scattering process inside the constriction. And as for the dynamic conductance spectrum of this blue curve, it's theoretically a curve from the Kummel model. You could see for the idealistic case of the one single isotropic gap, the number of subharmonics which depicted by this formula and the natural number n. And here, as I will present our experimental results. You could see several current voltage characteristics at the liquid helium temperature obtained by the break junction technique. And this dotted line is the same with the temperature a little more than Tc. So you could see the excess current and some foot structure, and this is should be Andreev regime, but while you readjusting the contact, you could obtain several any area you want, and area could change, and this change in area or transparency results in changing of normal resistance. You could see these curves are not the same. This blue and violet is the same, their dynamic conductance spectra presented here with number 2 and 3. But this sequential readjustment of the contact produced the several contacts with the different normal resistance, but as we could compare its dI by dV characteristic, you could see that the main peculiarities which have the maximal amplitude and marked by these shadow areas are nearly the same and have the same position. Since it's the most strongest peculiarity, we assume that it's connected to the fundamental Andreev harmonic with n equal 1. And if so, we should find the second and third harmonics, which also possible to do. And also we have some low amplitude fine structure, but it's the matter of the second part, and we attribute it probably to the appearance of bosonic mode in this compound. We could see that spectra are reproducible, and so if we take another sample of this neodymium 1111 compound and one of spectra which already the background is suppressed already in this spectra to enlarge the main peculiarities, the Andreev minima. We could see some seria and 1, 2, 3 probably for the large gap, and we could plot this data for this contact, it's red points, and for other contacts here, because we know this formula. So if we plot its position as inverted n number, it should be line goes to origin. Here you could see some structure near the foot, and probably in respect to other 1111 compounds we have studied, it should be connected with the small gap. If one suppress background here and plot it as was done in the right panel, you could see some structure, but it's good visible only the first and the second. The third, you should take the second derivative, but it also could be checked. But the problem is that it was the only contact where we could detect something near zero bias, but we could expect that it also some input from the small gap in this compound. But it's hard to say the same for other contacts. And here we take this spectra with temperature, and this inset show the position of subharmonic gap structure for the small gap, and here is result of this position. As we for the first and second Andreev minima, and also for the possible small gap, as we replot it to the temperature dependence of the order parameter, blue points is a large gap and empty is small gap, probable small gap, we could show that it could be fitted by the trivial Moskalenko-Sul temperature dependence by theoretical dependence by these green lines. And so it could be both gaps, but probably the input of zones, effective zones with a small gap in this compound are very small, the same as the conductivity. And the resulting data, you could see some statistical on the large gap temperature dependence, but for the small gap, as I said, it's only one. And here is BCS temperature dependence, and you could see that critical temperature is the same as in bulk resistivity temperature dependence. And I'm finishing with the data of the characteristic ratio. You could see some our old data by the break junction technique for other 1111 compounds, for the large gap and for the small gap. And new points are the stars for the niodium with hydrogen substitution. And you can see that it's nicely fit all this data. But one could say that probably it means that we have found nothing new. But from the other side, from the main point of view, the main result of this work, that due to this substitution, which introduced not only the electronic input, but the influence of the hydrogen atoms, we found that the influence of the effective bands with a small gap strongly decreased up to the total impossibility to detect it experimentally.
Could you please show the summary?
Yes, I should cancel with the second part of my talk with the bosonic mode, but if any questions, I could show and answer it after the session. These results were published by us, so you could also watch it as a paper. And here are results and conclusions for these neodymium 1111 samples. Thank you for the attention.
We will, just please brief question. Try to formulate short question.
Thank you for your nice presentation. Please return to your last slide that you showed. No, in your talk, make comparison between two sets of results, experimental. Yeah, you mentioned there is a good coincidence. I see that the scatter is here about 20%. What is the reason for this scatter of results? And in my view, it could have been related to different sizes of your break junctions, but you might have another explanation. Thank you.
Thank you. I could say that the size of junction it influence only for the normal resistance, and we normalize our conductivity spectra to its normal value. The normal value, I mean, up than Tc. So it should not have any influence, but this characteristic ratio is something as the first derivative of the function of the superconducting gap amplitude versus critical temperature. So as it's mathematically is the same that the first derivative, and of course when you make the first derivative of some experimental data, you every time got large noise, but here noise it's not very large.
Can we briefly say yes or no, or in detail discuss after the session, because we are late?
Yes, it's hard. Okay, if it was two questions, but for the normal resistance it's no, and here yes, because it's experimental uncertainty of this value and also Tc, both of these developed in this ratio in the scatter.
Okay, we thank the speaker for the presentation. Thank you.
Thank you.